Good evening. This is Professor David J. De Los Reyes. My lesson for tonight will be exact differential equation. So we are back to long video. I am now on the topic DE33. This is on the topic differential equation on my channel. Differential equation. The topic is actually a differential equation, and the subtopic is exact differential equation. I got a subscript number 3/3. I think this is my third lecture on the exact differential equation. Hold on, guys. So this is actually my third lecture on long video on differential equation. Okay, let's proceed, guys. The topic for tonight will be an evaluation problem of an exact differential equation. I will try to give you an example problem for tonight. Okay, let's proceed. We are given a problem, evaluate. We are given a differential equation. Quantity 6xy squared minus 3x squared closed quantity dx plus open quantity 6xy or 6x squared y plus 3y squared minus 7 closed quantity dy equal to 0. So actually we are given a differential equation, and since the problem says that the differential equation is an exact differential equation, later on we could verify if it is really an exact differential equation. Okay, let's try to bring out the solution. The solution of this number one step is actually to expand the given differential equation, because as we could see it, this is a pure a function of x and y. This is a pure x. So if we try to multiply this by dx, actually this is already directly integrable. For the second part, if an x and y combination, it's not yet integrable, but the second part, or the last two part, which is 3y squared minus 7 closed quantity dy, this is y function, this is dy, it is actually integrable. So if we try to expand, the expansion will be 6xy squared dx, the first one, minus 3x squared dx, the second one, plus the expansion of this, which is actually 6x squared y dy, plus, we combine this one now. Since the 7 is actually without any constant, we can combine this with the y squared. So this will be quantity 3y squared minus 7 closed quantity dy equal to 0. Then try to inspect the resulting expansion. On the first one, this is a pure function of x dx. So this is directly integrable. This portion here, this is a pure function of y, this is dy. So actually, this is also directly integrable. So we are now given a part of the solution. First one, second one, directly integrable, directly integrable. Okay. Let's inspect the first one here. 6x y squared dx. This one here, I will try to mark this with the blue one. Whether we like it or not, this is not yet directly integrable. So I make a markings over here, not directly integrable. Why not directly integrable? Because the dx, the differential thing here is x, and we got a y here, right? There's a y. So for the meantime, we could not integrate it. The second one, 6x squared y dy. If you try to observe it, it is also a combination of x and y times differential y. And I mark this one as also not directly integrable. Okay, let's proceed with the directly integrable. The integral of directly integrable ones, this one here and this, equal to, we will just copy this one. The integral of minus 3x squared dx plus the integral of this one, 3y squared minus 7 closed quantity dy. Okay, integrating this one, we bring out the negative 3. The integral of x squared dx is actually x cubed over 3. Power formula. First one here, 3 is constant, we bring it out, 3. The integral of y squared dy is also power formula. Y to the third power over 3 minus 7. The integral of dy is just y. So the last part is actually minus 7. The integral of dy is just y. Simplifying, the integral of those directly integrable, a part of the solution is actually negative x cubed plus y cubed minus 7y. These 3 cancels, right? And this 3 cancels. So it will remain just simply negative x cubed plus y cubed minus 7y. This is actually the first part of the solution. Okay, let's try to bring out those that are not directly integrable, NDI. Those not directly integrable is this one here, the one encircled by blue, and this one. Those not directly integrable is actually 6xy squared dx plus 6x squared y dy. I place an arrow over here. The sum of these is actually an exact differential equation. We will bring out the proof that it is an exact differential equation. M here is actually 6xy squared, and N here is actually 6x squared y. We are under the form the integral of m dx plus the integral of m dy. That is under the concepts of differential equation. So m here is actually 6xy squared and n is actually 6x squared y. And to prove that this the sum of these is an exact differential equation, we will take the partial derivative of m with respect to y, then take the partial derivative of n with respect to x. After taking the partial derivatives, if they are equal, we could say that the sum of these is actually an exact differential equation. Okay, let's proceed with the partial derivative. M is actually 6xy squared, right? Taking the derivative with respect to y. For the meantime, treat any x term on the right as constant. Okay? So if we try to take the partial derivative of m with respect to y, okay, treat 6x as constant. That's the rule, right? So we bring out 6x times the differential of y squared. The differential of y squared is actually power formula, right? So it should be 2y, and we are taking the differential or derivative with respect to y. This is times 1. So what will come out will be 12xy. For n, treat y as constant. Treat the product of 6 and y also as constant while taking the partial derivative. Therefore, the partial derivative of n with respect to x equal to, treat any constant in y as a simply constant, so we bring it out, so it will be 6y, and the integral or the derivative of x squared is actually power formula. We are taking the derivative with respect to x. The derivative of x squared is actually 2x. We are taking the derivative with respect to x times 1. Taking the product of this, it is 12xy. So as you notice it, the partial derivative of m with respect to y is 12xy, and the partial derivative of n with respect to x is 12x, also 12xy, according to the concept of differential equation, if these two values here are equal, we could say that the given directional, the given NDI is actually an exact differential equation. So I place it here. Since the partial derivative of n with respect to y is equal to the partial derivative of n with respect to x, and since they are equal, the NDI is actually an exact differential equation. Meaning, the sum of these is actually an exact differential equation. And there are two solutions on how to bring out the solution of this. There are two solutions. Solution number one, just integrate the integral of NDI. So solution number one could be equal to the integral of m dx. Take the value of m here, place it in. The integral of 6xy squared dx. But there's a concept over here that while you are integrating with respect to x, treat any y as constant. So the product of 6 and y squared are constant for the meantime. So we bring it out. So it will be 6y squared, the integral of x dx. So this will be 6y squared. Okay? Under normal integration, this is not allowed. But under exact differential equation, this is the concept. Right? Okay, so this should be 6y squared, the integral of x dx. The integral of x dx, it falls under the power formula. This should be 6y squared. Okay? We are just copying this one, x squared over 2. So the integral of those not directly integrable under solution number 1 is actually 3x squared y squared. Okay, let's try to bring out the second solution. The integral of those not directly integrable is also equal to the integral of n dy. This is n. We will copy this one, so this should be the integral of 6x squared y dy. For the meantime, while you are integrating, treat any x terms as constant. So actually, we could bring out the product of 6x squared, treat it for the meantime as constant. So if they are constant, we could bring it out inside the integral sign. So this will be 6x squared. Because if they are not constant, you cannot bring it out. But under the concept of exact differential equation, while you are integrating the integral of n dy, treat an x term as constant. That's why we bring it out. So this will be 6 squared, the integral of y dy. So it will be 6 squared, power formula, right? Y squared over 2. The integral of those not directly integrable, solution number 2. This is actually solution number 2. Okay? Is equal to 3x squared y squared. This one here is same as this. So actually, if you are on the examination, you could use this one or use this one. Or if you want to verify the correctness of your answer, bring out these two here. If they are the same, your solution is correct. Therefore, the solution of the given original differential equation, it will be the integral of those directly integrable plus the integral of those not directly integrable plus a constant c equal to 0. This one, we did this. It's the first one, right? We'll just copy. So it will be minus xq plus yq minus 7y plus the integral of those not directly integrable. I write it here, the integral of the differential of 3x squared y squared, okay, plus c. Why I wrote this one? Where did this one came from? It came from this. Because the meaning of this, if you try to take the differential of this, what will come out is this one. These two here. So to simplify it, it will just be the integral of the differential of the resulting 3x squared y squared. The integral of the differential of 3x squared y squared plus c equal to 0. Rewriting this one, minus x cubed plus y cubed and 7y. The integral of the differential of this, okay, if the integral goes near the differential sign, they will try to cancel out each other. So actually, this is gone. Okay. So this will be 3x squared y squared plus c equal to 0. Do you now know the significance of this? If you try to take the differential of this one, what will come out is this one. Those not directly integrables. The product, the sum of these, 6xy squared dx plus 6x squared y times dy. You got it? This is the exact differential equation part, this one. If you try to take the differential of this, the expansion is actually the given value NDI. Okay, and how did we arrive at this one? We present two solutions. The integral of m dx or the integral of n dy. Okay, so this is the directly integrable, the first one. This is the not directly integrable, and luckily it is an exact differential equation. Oh, that's it, guys. That's how we attack the problem under exact differential equation. It's an easy one. You just expand. There will be terms that are directly integrable, and there are terms that are not directly integrable, and luckily those not directly integrable is actually an exact differential equation. And our problem here is to bring out the correct terms in which, if we try to take the differential, what will come out is this one. We bring out two solutions, the integral of m dx and the integral of n dy. First solution is actually, the answer is 3x squared y squared. The second solution is same, 3x squared y squared. So meaning, this expansion is actually the differential of this term here. So I place it here, it should be the integral. It should be the integral of the differential of 3x squared y squared. Integral goes near the differential sign, they will try to cancel out each other. So the final answer will be minus x cubed plus y cubed and 7y. The differential vanishes because it goes near the integral sign, right? So it will be 3x squared y squared plus c equal to 0. That's it, guys. So for those who are taking up differential equation, this is for you guys. This is the long video ones. If you are subscribing to my channel, sometimes I am presenting problems under exact differential equations in the short video form. Okay, good night. This is Professor David J. De Los Reyes. Good evening, Los Angeles.